Hey everybody, welcome back to Calc 3 Online. So the plan for today is to actually just talk some more about curvature specifically. And last time I just really showed you those two formulas, but today I want to kind of make sure I give you like a little bit more of an intuitive idea of what curvature really is. And I'm also going to actually prove to you why the two curvature formulas are actually equal. But I want to start with this problem. So this has always been kind of like a weird result. So if you have a circle of radius A, it actually has curvature 1 over A. So there's this property in math that circles have like reciprocal curvature to their size. And if you think about the problem we talked about just briefly last time, that bigger circles with larger radiuses have less curvature, and smaller ones with super small radius would have higher curvature. It kind of makes sense because if you do like 1 over a big number, right, you get a small number. And if you do 1 over a small number, you get a big number. So that kind of checks out. So to start off, we got to write a parametric equations for a circle. And the way we do that is x equals a cos t and y equals a sine t. And if you literally just do out x squared plus y squared, you'll see that it equals a squared. But that, this is the circle of radius a, and so these are the parametric we use. And so basically we're just going to use the 2D curvature formula, and we're going to go crank this thing out and show that we better get, 1 over a over here. It's going to equal 1 over a. So we're going to need r prime. So let's start with that, I guess. R prime of t will equal minus a sine t, a cos t. Then we need, might as well do the magnitude of it. The magnitude will be, basically you're going to get a squared sine squared plus a squared cos squared. So then when you take the a squared out, you're going to be able to get the square root of like a squared times a 1 because of sine squared plus cosine squared. And that square root of a squared is the absolute value of a, which is a classic algebra 2 mistake to drop the absolute value. But a is positive, so we can really just write a because it's the radius. So that is the magnitude of r prime. And then we need to know t prime. So let's start with t. T, capital T, it's r prime over the magnitude of r prime. So we have all those things. So we got 1 over a, which is the magnitude part, times the vector minus a sine t, a cos t, which basically just, if you multiply the 1 over a in, you're just going to kill the a's in front, and you get minus sine t cos t. So then t prime of t would be minus cos t and minus sine t. And we also need the magnitude of that thing. So if you do the magnitude of this, it actually is just going to work out to be a 1, which is nice because you basically just get, cosine squared plus sine squared. And that's a 1, the square root of 1 is 1. And so if you go and take your magnitude t prime, put that in there, right there, you get 1. And if, I'll do different colors actually, put that in there, you get 1. And then if you put in your magnitude of r prime, that's a. And so you really get 1 over a. All right, these are just good kind of concept questions related to curvature. So if I was asked to sketch a graph which has 0 curvature and one which has a steadily decreasing rate of curvature, for 0 curvature, I might just use a line. You could just take like y equals x, something like that, right? Lines are things that don't have any curvatures. They're like the curve of curvature 0, that they can actually sometimes be considered a curve, just ones that have curvature 0. Depends on the book you look up. Some books just don't even count them as curves too. But I kind of think of them as curves with curvature 0. Something that has steadily decreasing curvature could be like exponential, we'll say. So if you want to do steadily decreasing rate of curvature, you could do like, e to the x. So it kind of turns quickly, but then as you go on, you're going to get it's going to kind of start to straighten out and go like, straight up almost. And when it's doing that, it basically looks like a line. So this thing curves a lot in the beginning, and then it just flows down, and it's just going to decrease. There's other options too. You can do like, there's like, polar graphs where you have like spirals, like things that turn quickly like this, but then as time goes on, they kind of unravel. So that would be something that has decreasing rate of curvature. Anyways, so if we take a look at this picture, so in this picture, one of these is a function, and the other is a graph of the curvature. And the question is, which one is which? And this is kind of hard to read. So this is 1 down here, and this is 2 up there. So if you look at it and think along the lines of kind of this exponential idea, right? If this was the function, right, then the function would have like not much curvature over here or over here, because the quadratic's gonna straighten out. And here, where its vertexes, it's turning a lot and rapidly. So right here, it should have the most curvature. And that is exactly what's happening. So if this is the function, which it is, this is f of x. So f of x is this graph right here. Parts like here, it turns a lot. That's why the graph of the curvature is at its highest part. And then over here, there's almost no curvature, which is why it's flat lines and there, because, if you kind of think of like tangent lines and stuff, the tangent lines look, practically the same as the curve there. Whereas if you do a tangent line here, you can get like, you can get one that's like, along the x-axis, and it's very different than the curve itself. So we've got, this red thing, the graph of the curvature, and the blue one is a graph of f of x. All right, so same kind of thing. You've got choices A and B. So B1 is the blue one there, and A is the red one. And the question is, which one is f of x, which one's the curvature? And kind of same thing here. What I would do is sort of try and think about specific spots that kind of match up together, I guess. One of them that's kind of unique is like right here and here. So, on this blue graph, it's concave up, and then all of a sudden it's concave down, and then it comes concave up again. But if you go from concave up to concave down, there has to be a point right in, that spot where, right there where it's like straight. It's looking for a fancy word, but we'll just go straight, because that's what it does, right? If it's like you're concave up and then you're concave down, somewhere in there it's like a perfect line. It's kind of like, it has to pass through a straight point before it moves back down. And so that means that like somewhere in here and here, there's like a curvature point of 0, which is exactly what this red graph is showing. You also have things where like this has a lot of curvature. There's like a lot of turning happening on the blue one right there, so it spikes on the curvature graph. And then like as you go over here, it's kind of like flatlining, which is why the curvature graph is sort of decreasing again. But basically, you've got you got this red graph, and that again is actually curvature. And then you got this blue graph, and that one's the function. All right, so for this example, first I want you to think about what this vector valued function would map out. So you have this thing a cos t, a sin t, and bt. And a and b are just some real numbers. And so since these are the same in the x and y, xy plane, it's going to just look like a circle of radius a. Those are the exact same parametric that we use right back here. And then if I let z just be some scalar on t, basically all that's going to do is it's going to take my circle and, in a sense, pull it like out of the plane. So what this kind of looks like is you have like a circle, and then it just pulls it out of the plane like this and this and this. And it would even go down, right? I'm a horrible artist, but basically it's a circular like spring that is sort of infinite in the z direction like that. And then it, in the xy plane, it looks literally like a circle of radius a. I felt like my circle was good, and then I can't write the letter A. But that's what it looks like in x and y, and then the bt just brings it up and down in z. So something like this, the curvature of it should be constant, because, and that's another thing I kind of didn't really mention here, but the curvature for a circle is constant. It's this specific constant. But it makes sense that it shouldn't really be a function of t. It should just be like, you have these t's in here, but somehow if you compute the curvature, it should just work out to be a constant. So I want to show you that it actually is. It's just something that is in terms of a and b, and that's because like as you move up this thing, it's always just turning the same amount, forever and ever and ever, however much you want to go. So I'm going to use the 3D one. So I'm going to need r prime, which is minus a sine t, a cos t, and b. I'm going to need r double prime because I'm going to cross the two of those. So that's minus a cos t, then minus a sine t, and then 0. So then if you do r prime cross r double prime, all right, actually I'm just going to tell you what you get, because at this point I think you should be able to kind of do these things on your calculator anyways. If you need help doing these on your calculator, I am more than happy to show you how that works. All right, so that is what you should get for r prime cross r double prime. And then you need the magnitude of r prime. So let's do that. The magnitude of r prime is going to be the square root of, it's one of these where it's square root of a squared sine squared plus a squared cos squared. So then if you do the thing where you can factor out a squared, you're going to get sine squared plus cosine squared here, and that can go to 1. So you're really just going to get an a squared times 1 plus b squared. So Then you also need the magnitude of r prime cross r double prime. And that's kind of a mess, but if you do it out, you basically have to, I guess I'll just write it. I should have enough room here. So you'll have a squared b squared sine squared, and then you'll have another a squared b squared, but then it'll be co-squared. And then you'll have an a to the fourth. And then you can do the same trick where you have this a squared b squared in both. So you can take those out. And you have a squared b squared plus a to the fourth now, because you use the trig identity in there. And the curvature is just this magnitude of r prime cross r double prime over the magnitude of r prime cubed, and the square root of a squared b squared plus, whoops, so close, I blew it at the last second. So this thing over the square root of a squared plus b squared cubed, that is an element of the real numbers. It's just a constant, which is what you would think. So it really is just a number. That's all I'm saying. And that's kind of weird, but I hope it makes some sense. The idea is like you're always sort of curving the same amount. There's no point where it's non-constant. It's just a fixed curvature, dependent on what these A's and B's are. All right. The last thing I want to talk about is kind of a big one, and it is why these two things are the same. They look very different, but these two K of T's are the same, and so these should be the same. And basically the problem boils down to if this thing, right, is equal to this, there's some similarities. Like you have an r prime of t on the bottom. Here you have 3, right? And so for some reason, capital T prime needs to equal this over 2 more of these, right? Because if you do like, K of T equals 1 over magnitude of r prime times magnitude of r prime cross r double prime over magnitude of r prime squared, right? Then you would get, this. And so really, the idea is, why does this part right here, why is this equal to the magnitude of t prime? And so what I'm going to show is that really this is equal to this. And because of that, then these two things are equal. That's like the idea. Because then you can just take this as t prime, you put it in, here, and you get this, or you could unpack that and you can get this one. They would be the same thing. All right, I need a new blank page for this because it takes a little bit of time. All right, so this thing is a good one to go over, by the way, just because there's like a lot of vector calculus tricks in here that I think are good to see. So it's not just meant to literally prove that these two things truly are the same. I like it because along the way, we're going to pull on some properties of some vector calculus we've learned that is actually really important. So let's do this thing. So starting off, I'm just going to remind everyone, so you got capital T of t is r prime over the magnitude of r prime. It's going to be important. And we also had that this arc length function, which is this integral from a to t, magnitude r prime, really of u, because it's like a dummy variable, du. That's another thing that we have. And from this, we talked last time about if you take ddt of both sides, then you would get that ds dt is equal to the magnitude of r prime. Okay, these are just like things I'm going to kind of use along the way, is the idea. All right, so we have r prime. If you just take this and you rewrite it for r prime, basically just multiply both sides by the magnitude there, you would get the magnitude of r prime times t. And then you could use this fact, right? And ds dt is the magnitude of r prime. So we could also swap ds dt in there for magnitude of r prime. We need r double prime because of the cross product in the curvature formula. So I'm going to take a derivative of this first derivative here. So that would be basically a situation where we need the chain rule because these are both functions of t. So we would have d squared s dt squared, and then times t plus ds dt times t. Oh, sorry, t prime. So that's my product rule. Then I'm going to do r prime cross r double prime. And I'm just going to kind of write in what r prime is, and then crossed with r double prime. Okay. And for a situation like this, you can multiply, in a sense, sort of distribute in here. And so we would get ds dt times t cross d squared s dt squared t. And then we get plus ds dt t cross ds dt t prime. All right, so basically just distributing in a sense. Then this is an important situation. So actually this whole thing would go to 0. And the reason that goes to 0 is you're doing in there a t cross t, and that would equal 0 if you just think of how the cross product works with like the area. So if you have like a vector, like that one, let's say is, that's like t. You can even do like a scalar on t, like 2t, which is what we have there. And then, there's no parallelogram that's formed by these. And the magnitude of the cross product is that area of the parallelogram. And so since these are parallel, their cross product is 0 because it forms like a parallelogram of dimension 0 is the idea. So that whole term just goes away because of the geometric understanding of what the cross product is. So basically this thing is my r prime cross r double prime that I'm going to work with. So I'm going to kind of move that up here. So we got r prime cross r double prime. I'm going to need to take the magnitude of this thing as per like the formula for cross product. And the magnitude of the cross product, if you use like the magnitude of this cross product, if you use the that sign formula, right, it would work out to the magnitude of like the first vector, ds dt, and then times the magnitude of the second vector, ds dt t prime, times the sine of the angle between them. All right, so this is just literally the formula for the magnitude of a cross product. Some of this can kind of be simplified because you can take like a ds dt out of both of these. So you would have like a ds dt squared. And then you would have like a magnitude of t here, but the magnitude of t is, really just 1, because that's, by definition, the magnitude of this is its length 1. And so that part kind of disappears. You still have the magnitude of r, or t prime. So I'm going to write that. And then this part is also kind of weird. So you have this sine theta is actually also a 1. And it's a 1 because I'm going to write this, but I'm going to have to erase it because I need more room. But we proved something before where if the magnitude of a vector, which in this case is really like the t, so actually let me just write that. If the magnitude of like some vector t is like a constant, which in this case it's 1, because it's a unit tangent vector, then we proved that like t dotted with its derivative vector was 0, and that came out of like that circle problem. And so the idea was like you have a vector and then you have like a tangent vector to it, and they met at 90 degrees. So the angle in there was pi over 2, or 90 degrees. And if you take the sine of that pi over 2, then that also simplifies down really nice. So this is really what we have happening here. So I'm actually going to now have to erase all this, but we proved this thing in red that I'm erasing a little while back, so I'm using that. So now I have that the magnitude of this thing is ds dt squared times the magnitude of t prime. And so now I'm basically ready for the punchline. So if I use this, ds dt is the magnitude of r prime. So I can do magnitude of r prime squared times the magnitude of t prime. And we know that this is equal to this, right? So if I just divide both sides by the magnitude of r prime squared, then I get magnitude of t prime equals magnitude of r prime cross r double prime over magnitude of r prime squared. And that is what I wanted to show. That was what I was talking about over here is really sufficient. I needed to show that the magnitude of t prime is equal to this thing, which is what I just walked through here. It's kind of a cool problem. It uses like this geometric idea of the cross product, which is really important. It uses stuff with arc length is in here and how you can go from this to this. It uses that sine theta formula for cross product, or magnitude of cross product. It has tricks where things like knowing that the magnitude of t is 1 because it's a unit tangent, and then realizing that actually there's like a pi over 2 angle in here, so the sine of theta goes away to 1. Lots of cool tricks. Don't worry too that if I'm ever going to like test you on this would definitely be like a bonus problem, but I think it's a good problem to see just because of all the tricks involved.